Hello, class. So first things first, I'm going to leave my video off today because my slides are a little bit crowded and I don't have space for my talking head. But I'm starting today's videos with a look back on a slide I showed you on day 1. And this was our approach to class. So we were going to take an interdisciplinary look at macromolecules before we move on to the functions of a cell. And so we've just talked about proteins, a type of macromolecule, and we examined chemical principles that guide how the protein folds, and we looked at how protein folding was absolutely critical to its function. Today we're going to pause on macromolecules and talk about basic physics and use these to predict the behavior of molecules or reactions in a cell. Specifically, we're going to take a deeper look at the rules that determine whether reactions are spontaneous or not, and how enzymes, a group of proteins, speed up spontaneous reactions. And why we're doing this week is because in lab, we're going to look at how pH and temperature affect enzyme activity. Okay, so let's start by talking about energy. Energy is the capacity to do work or supply heat. And it comes in two forms. It comes in a stored form called potential energy, and another form, which is movement, the energy of movement, which is kinetic energy. And let's talk about this with this analogy of a waterfall. Okay, so the water at the top of the waterfall has high potential energy. It's got a lot of energy stored up, and the water at the bottom has low potential energy. If you're looking at this waterfall, you can also identify some forms of kinetic energy, right? The water is moving down the waterfall, and this is a form of mechanical. But if you've ever seen a waterfall or been by a waterfall, you can hear the sound of it crashing against the rocks, and this is another form of kinetic energy. You can also maybe feel that the water is warmer down here as it crashes into the rocks at the bottom as that potential energy is transformed. And what you'll also realize when looking at a waterfall is that energy is always conserved, okay? And this is the first law of thermodynamics. Energy is conserved. It can't be created or destroyed. It can only be transferred and transformed. So the potential energy here, as it's getting converted from high to low, it's being transformed into that kinetic energy. It's moving, it's creating sound. Okay, so what does potential and kinetic energy look like inside a cell? Potential energy has to do with position, right? The top or bottom of a waterfall. But in molecules, it's the position of shared electrons. So let's take a look at this image here, which is depicting different types of covalent bonds. And over here, we have a polar covalent bond, in which it's a bond between an electronegative atom and oxygen and hydrogen. And as we've talked about, electrons in this bond will spend more time around the electronegative atom than it will around hydrogen. This forms a very short and strong covalent bond, okay? On the other side of the spectrum, we have our non-polar covalent bonds, in which this is between carbon and hydrogen, but these shared electrons are shared evenly, and this results in a long but weak, relatively weak, covalent bond, okay? Now, this is related to potential energy because these long, weak bonds, they have the highest potential energy, okay? And then these polar covalent bonds, they have the lowest potential energy. And in a couple slides, I'll talk about an analogy for this, okay? But let's talk really quickly about kinetic energy in a cell. Now, chemical reactions in a test tube, the potential energy is converted to kinetic energy, and that kinetic energy is light and heat, and it's usually lost through dissipating out of the test tube. In a cell, this potential energy is converted into ATP, which is a form of cellular currency that does work, and we'll talk about this more in the next couple podcasts. Okay, so we've talked about energy, and we've talked about chemical reactions. And chemical reactions are either spontaneous, meaning they can occur without the input of additional energy, or not spontaneous. And this depends on two things. It depends on if the reactants have higher potential energy than the products. Okay, so let's take a look at what that might look like. So here we have hydrogen gas, 2 molecules of hydrogen gas, and a molecule of oxygen gas. And this can be converted into 2 water molecules. Now, in this reaction, we have all of our molecules, the hydrogen gas and the oxygen gas. These are actually non-polar bonds because the electrons are shared evenly. They're even shared equally between the 2 oxygen because they have the same amount of electronegativity in this molecule of oxygen. So these are shared evenly, meaning that these are non-polar and they have high potential energy. But as these are converted to water, the electrons are now shared unevenly. And so oxygen has more pull on these electrons, and these are going to be shorter, stronger bonds. So in this example, the reactants over here have higher potential energy than the products. And this reaction is spontaneous, and if it was in a test tube, it would release energy. And this is actually what happened in the Hindenburg disaster in the 1930s, where hydrogen gas and oxygen gas interacted. This formed water, and this massive explosion happened because energy was released in the form of heat and light and vaporized the water that was produced and caused a big explosion. Okay, so before we move on, just by talking about this, sometimes students have a hard time grasping the idea of potential energy stored in chemical bonds. And so if this makes sense to you, maybe just skip this analogy. But here's an analogy to help you grasp this a little bit better. Okay, so I call this the magnet analogy. Okay, so here we have a magnetic train. And this is something that my kids played with when they were little. And this magnet here represents a non-polar covalent bond. It's relatively weak, and so if I wanted to detach these 2 trains, right, it's a weak magnetic force, they would be relatively easy to pop apart. I wouldn't have to put very much effort into it. Here's me, this is my relaxing on the beach. This isn't actually me, but this requires very little energy. This is in contrast to some of these stronger magnets that you might work with in some industrial purposes. And these represent these polar covalent bonds, right? These have a stronger magnetic force, and they require much more energy to break apart, right? This is, for example, if you were to run up one of the Moros. Okay, let's put these in a chemical reaction, okay? So we're talking now about overall energy expenditure. So it's going to take me relatively little force to break apart these 2 trains, okay? And actually very little energy to create these bonds because they're kind of drawn to each other, right? So overall, very little energy expenditure. This is in contrast to if the reaction went the other way. If I wanted to break apart this really strong bond, I'd really have to use a lot of energy, and then I'd have to pick up these 2 pieces of these trains and put them together. They're not naturally drawn together. And so overall, this is going to take a lot more energy to break and create a bond. And so I'm really running up the hill. So this is another way, hopefully this analogy works, or you can come to me and we can talk about another analogy that might help you remember that these non-polar covalent bonds are weak and that they have high potential energy. Okay, what's another thing that makes a reaction spontaneous? Okay, the second thing is that when products are less ordered than the reactants. So here's an example of that. So we have a glucose molecule here, and in glucose, we've got a lot of carbons in a ring structure that are bound to oxygen and hydrogen. And we've got a bunch of oxygen molecules. And in this reaction, this will combust, and the energy will be released in the form of heat. But also what you notice is that here we had 1 molecule of glucose, and so it was really organized. And now all of the glucose has been converted into CO2. And so there's a lot more molecules. This is way more disordered and less organized than the sugar. Another example that we've already talked about is the hydrolysis of monomers from a polymer. And so here we put in water and one of the monomers comes out from this polymer. Okay, so these are two examples in biology of when products are less ordered than the reactants. Okay, and this matters because of the second law of thermodynamics. So this is a principle in physics that entropy of a closed system or universe will always increase. So disorder will always increase. And so here's a picture of this happening. This was my son when he was very little, and this was a house we used to live in with a lazy Susan. And you see the chaos of the system will always increase in disorder, and it will require a lot of energy for me to put back everything into the lazy Susan and probably toss out the spaghetti because now it's all over the floor. So just an example. Okay, so we've talked about when a reaction is spontaneous. And scientists have developed this equation called the Gibbs free energy equation that takes into account these principles and allows us to determine whether a reaction will occur spontaneously. So it takes into account the difference in potential energy between the reactants and the products, and the difference in the order or the amount of order between the reactants and the products. So let's talk about this first point. So the difference in potential energy. In Gibbs free energy equation, this is called enthalpy, which is also termed as the heat content, right? So if this was to be in a chemical reaction, how much heat would come out? And this is represented as delta H. And the way I remember this is because enthalpy, has an H in it. And so if energy is released, then this delta H value is negative. And if energy is taken up, if it requires energy, then this delta H value is positive, right? So if it's released in a reaction and let's say it's in a test tube, then the test tube is going to get hot and this value of delta H is going to be negative because energy is coming out. The difference in the order between products and reactants is represented as entropy, which is basically disorder, and it's represented as delta S. And if disorder increases, the value is positive, so that's a good thing, thumbs up. And if disorder decreases, the value is negative. Okay, now I'm not going to really ask you to tell me for an individual example. For example, if I were to give you reactants and products, I'm not going to have you predict whether those are positive or negative. We're going to focus on the overall equation, which is the sign of this delta G. And this is Gibbs free energy equation. So delta G equals delta H minus T delta S. And you won't have to memorize this equation, but just know what these values represent. Okay, now here's the part I really want you to pay attention to. This is the delta G values, okay? And these are what determine whether or not a reaction occurs spontaneously. And delta G is the free energy. So if delta G is negative, okay, and this would happen if the reactants have high potential energy and are very ordered, and we come down here and the products have low potential energy and there's more disorder, okay? So if delta G is negative, then this reaction is spontaneous, and it's also called exergonic, okay? And so I remember this because I X the energy out. I don't need to put in energy to get this reaction to occur, okay? So on this chart here, we're going to work with this a little bit in class, but we have free energy on the y-axis and the progress of the reaction free energy on the y-axis and the progress on the x-axis. Just want to point out this progress does not necessarily mean time. In contrast, if delta G is positive, so the reactants have low potential energy and are disordered, and we want to build something that's really ordered with lower potential energy, then the delta G will be positive. And this reaction is not spontaneous, and it's going to be endergonic. So again, exergonic means to X out the energy, and endergonic for energy if you wanted to remember those terms. Okay, so again, a hint for the quiz, definitely know what these delta G, the signs of delta G mean. So whether it's negative and spontaneous or positive and not spontaneous. Okay, but why is this? Why is when a delta G is negative, why is that spontaneous? Okay, so let's think about it with math. Okay, so if the reactants have a higher potential energy than the products, so they have start with high potential energy, then the delta H is going to be negative, right? They're going to have higher heat content. If the reactants are more ordered than the products, and so we're going to create disorder at the end of the reaction, then the delta S is positive. And if we have this reaction, this imaginary reaction, occur at 1 degree Kelvin, then -5 minus plus 15 is -20. So that's a negative delta G value. And these are both examples of parts of a reaction that contribute to spontaneity. Okay. And I just want to point out here that the hydrolysis of ATP into water, so ATP is this high energy molecule. We'll talk more about it in the next video. When this is hydrolyzed, you get the detachment of one of these phosphates here. And this reaction is very spontaneous. It's highly exergonic. And then the delta G value is negative 7,300 cal per mole. So there's a huge amount of energy. And actually, we're going to couple this exergonic reaction to power not spontaneous reactions. Again, more in the next video. But let's take a look at these positive delta G reactions. So in these reactions, the actually have the higher potential energy. And so the delta H should say positive. Let me just correct that. So the delta H is positive. If the reactants are less ordered than the products, then the delta S is negative. Okay, so we have 5 for a low potential energy starting point and -15 for a disordered starting point. So when we plug this into this equation, again, I'm just saying this reaction's occurring at 1 degree Kelvin, then 5 minus -15 is actually 20. And this reaction is not spontaneous or endergonic. If only one part of the reaction is favorable, then the equation is really useful. So I was just talking about generalities here. So for example, if disorder is still positive, then it's more likely to occur and be favorable at higher temperatures. So that's the relationship with Kelvin. So these are just some examples to help kind of clarify how this equation works. But overall, you should be able to understand kind of what the values of delta G means, what the individual letters in the equation represent, and when a reaction is likely to be spontaneous. And we'll talk more about this in class. Okay, so we were talking about whether reactions occur spontaneously, but even if a reaction occurs spontaneously, it may not happen quickly. And so for most reactions to proceed, one or more chemical bonds have to break and others have to form. So to do this, substances have to collide in a specific orientation that brings electrons involved in this chemical reaction near each other. And so both higher concentrations of the molecules in the chemical reaction and higher temperature both increase the likelihood in the number of collisions and increase the reaction rate. And that's just shown here. So here's reaction rate on the y-axis and temperature on the x-axis. And you can see as you increase temperature, the reaction rate becomes faster. And then here is showing the relationship between concentration and reaction rate. As you increase the concentration of your reactants, you increase your reaction rate. And this is because we're increasing the likelihood that two compounds can come together. As we'll talk about in the third video, protein enzymes can also increase the reaction rate. So this is different from whether or not a reaction is spontaneous. So this is talking about how fast things occur, not whether they occur. So in summary, whether a reaction occurs spontaneously depends on potential energy stored in chemical bonds, with higher potential energy in nonpolar bonds compared to polar bonds, and also increasing disorder. And an example of this is a hydrolysis reaction where you're releasing a monomer versus a reaction that decreases disorder, which would be condensation and the building of a polymer. Whether a spontaneous reaction occurs quickly depends on concentration, temperature, and enzymes. So that's it for this video. And in the next video, we're going to talk about how to get those non-spontaneous reactions to occur. And then the last video will be how enzymes help with chemical reactions.